During the late 1700s, a man named Neville decided it would be a good idea to measure the density of the Earth. This would be rather useful for a lot of different reasons we'll come to. This is a litre of water.
It's not.
Have you got any water?
I do!
Ah. This is a litre of water. You could say it's got a specific gravity of 1, which means that litre weighs pretty much 1 kilo, and therefore 1 metre cubed would weigh 1,000 kilos. Nice and easy. Volume against density. What though if you want to measure the Earth? How's that easy? That hasn't got a specific gravity of 1. You need to measure this density. How are you going to do that? So Neville suggested that if you could measure the density of a mountain, well, you could scale that up and measure the density of the Earth. The crux of this was, if you have a plumb line, have we got a plumb line?
No.
Okay, how about a bit of string? Ooh. And a weight of some kind?
String?
String.
Weight?
Weight, what have we got?
I've got a staple gun.
That will work just perfect. Okay, so if you can measure the effect the mountain has, the mass of the mountain has on a plumb line, you can work out its density, and you can work out, well, the gravitational pull of objects, and you can scale that up and work out the sun, the moon, and other celestial objects. It turns out this experiment would change mapping forevermore. Insert dramatic music here. Now, Isaac Newton was kicking around at the time, and he said this was a bit of a silly idea, it wouldn't work. He even said
gravitational effects are only discernible on planetary scale.
Which is wrong, because even by his own calculations at the time, well, you would have an effect. So Neville Maskelyne predicted that actually you could use modern instruments to measure the effect of the mass of a mountain on the plumb line. They just needed to find the perfect mountain.
So what's the perfect mountain, and why?
The perfect mountain is one that stands alone, so therefore it's not affected by any other mountains behind it. It's just one standalone mountain. They decided on one called Schiehallion in Scotland, forgive the pronunciation. Now our budget doesn't quite reach that. We're not quite there yet as YouTubers, so we decided to come to Beacon Hill in Berkshire. This was set to be a groundbreaking experiment. You see, Newton's theory, the gravitational theory, wasn't disputed, it just needed to be measured. And with this experiment, well, you could take your plumb line, you could go to each side of the mountain and measure thousands of different points of how much the mass or the density of the mountain changed the direction and the angle of the plumb line, and therefore you could measure, well, gravity. There was just one more thing they needed to do to get this going, and that was to measure the volume and density of this mountain, not this mountain. Charles Hutton, Reuben Burrow led a team of hundreds of labourers, and they were going to measure thousands of different points, angles, direction, triangulation of the entire mountain. And you can imagine, we're in Scotland, not Berkshire. Wind, rain, weather coming at you from every direction. This isn't going to take a short amount of time, and it didn't. It took at least 2 years. Now on the north side and on the south side, plus I think a bovey, they constructed some platforms to take their plumb line readings, and they took a lot of readings over a long period of time. But as we've said, well, the key here was measuring, for Hutton, the volume of this mountain, and he did that by triangulating thousands of points and measuring different heights all over this mountain. He split it as well into vertical prisms. To get around this and make sense of these thousands of data points, he decided to draw lines between values of the same height. Now, to do this, he would then align it along with the prisms, the vertical prisms he's made, and he noticed something quite spectacular. Insert revelation music. All of a sudden the map came to life. The hill stood out as if it was 3D, but it wasn't. It was just on a plain, flat piece of 2D paper. Hutton had created a contour line map, which he had no intention of doing. He just came here to measure the volume and the density of this mountain. Hutton had created the contour line. That's not completely true. In fact, contour lines do go back much further than that, but not as far as I can find above water. You see, contour lines were super useful in places like harbours and ports, so you can help navigate boats away from dangerous areas underground that were not seen. And again, they did that using a plumb line, but not in the same sense as plumb lines we've been using for this mountain slash hill in Berkshire.
And probably definitely not using a staple colour.
Yeah, but nevertheless, contour lines were now on the cards. The fellows working on this project opened up more questions. Medals were given for their work, and confirmation of Newton's inverse square law of gravitation had been confirmed. And of course, as a side bonus to this project, well, we came up, perhaps not with the original idea of contour lines, but perhaps a new way of mapping above the ground, which would include contour lines and help us give the 3D familiarity that we take for granted today on the OS map. In fact, they came to the conclusion that the Earth was 4,500 kilograms per meters cubed in terms of its density, which is only about 20% out from today's accepted 5,500 kilograms per meters cubed. In fact, Charles Hutton went on to suggest that the mountain that they spent a lot of time at was actually around half that, 2,500 kilograms per meter cubed. And he said, well, the difference was that the Earth itself, the centre of the Earth, must contain more heavier metallic elements and such. How right he was at the time, which is pretty groundbreaking considering that was a late 1700s. Fascinating stuff. I have been Paul.
And I have been Rebecca.
And thanks for watching. We'll see you this time next week.